Yes, my name is Rinu Boney, and I'm a PhD student at Aalto University. I also work part-time as a researcher at Curious AI, and I'm going to talk about sample-efficient deep reinforcement learning. So I'll begin by introducing reinforcement learning and how to solve reinforcement learning problems. Then we'll move to something called model-based reinforcement learning. I'll talk about why model-based reinforcement learning is important, and after that, I'll talk about my latest work on model-based reinforcement learning with denoising regularization and share some results. And this is joint work with my colleagues at Aalto and Curious AI. So to put simply, in reinforcement learning, you just want to learn what to do so that you can maximize your rewards. It is usually formulated as follows. There's an agent and an environment, and the agent does some actions to the environment, and the environment changes, and then the agent is able to observe things from the environment and also get a scalar reward value. For example, if I am the agent and this is my environment, I'm talking in the environment, that's the action I'm doing. But I can observe the expressions and the changes that goes through my environment, and I can infer my reward from these observations, and I continue to do my actions such that I get good rewards. And the goal of the agent is to maximize this reward. There's something called the reward hypothesis in reinforcement learning, which means that any kind of problem can be formulated within this framework. Let's look at some examples to better understand this formulation. So in Helsinki, you have these city bikes all around the city. Assume that such a system does not exist and you want to introduce this kind of city bikes. You have to make a lot of decisions to introduce this, how much bikes to purchase, where to allocate it, how to reallocate these bikes, and you observe the usage and availability of these bikes at each station. If there's a city bikes AI, then it can decide for us what's the optimal amount of bikes to purchase, how to reallocate them. And by looking at the patterns and trends of usage of these bikes, it can automatically reallocate these bikes. The objective of such an AI could be to maximize profit. Another simple example is chess. So if you want to build a chess AI, it makes moves with its piece, and the opponent makes a move, and it's able to observe the current state of the board, and the objective is to win the game, of course. To look at another example, this is a cheetah robot from Boston Dynamics. If you have such a robot and you want to make it run as fast as possible, then you want to design a controller that applies torques at the joints of this robot, and you can observe what changes, so how the position and velocity of the robot changes, and how the angles and velocity of the joint changes, and so on. And the goal of such a controller is to run forward as fast as possible. So within the setting, you want to learn a controller that can run forward as fast as possible. Now that we've introduced reinforcement learning, how do we solve these kind of problems? Humans have gained a lot of expertise in these kind of problems over a lot of years. So it makes sense to somehow use human knowledge in these problems. There are two different approaches you can take to solve these kind of problems. One is expert systems and the other is learning systems. So in expert systems, you human engineer or you manually come up with solutions to these kind of problems. And you hand code your solution into algorithms, and you can just run this algorithm to solve this problem. But this is a lot of work, and you need people with a lot of expertise for this particular problem. And even these experts may not be familiar with all kinds of situations that could happen within the problem. So these kind of expert systems are limited to the expertise of the humans who designed it, and it's limited to those hand-coded solutions. On the other side, we want learning systems to learn solutions to these problems from scratch. And these kind of learning systems could potentially generalize to new situations, and it could come up with solutions to these problems in a novel way that even humans couldn't think of. So manually solving all these kind of reinforcement learning problems does not scale because it's bottlenecked by human knowledge and time and productivity. So we have to use this human knowledge in a more scalable way. And so what we need is a simple algorithm that can reliably learn to solve these kind of problems with little or no human intervention. So the human knowledge can be used to design these kind of algorithms rather than to independently solve each problem. So these kind of algorithms need resources, and the fundamental raw material for machine learning algorithms are computation and data. And computation continues to get faster and cheaper, so it makes sense to develop algorithms that can maximally leverage these computational resources. And when it comes to data, collecting data is really expensive. And it's often the case that you don't have a lot of data. So if you introduced such a Helsinki city bikes system, after the first day of usage, you have to be able to make decisions immediately on the next day. So a good algorithm should be able to understand that there's a lot of demand at the city center and a lot of bikes have to be refilled frequently at the city center. So if an algorithm takes like months or years to figure out that a lot of bikes have to be there at the city center, then it's just not a good algorithm. So we need algorithms that are able to make decisions as fast as possible with a very few amount of data. And this is called sample efficiency. And that's mainly my topic of research. So I'll be focusing on that. So what are these existing reinforcement learning algorithms? Existing reinforcement learning algorithms can kind of be separated into two types: model-free reinforcement learning and model-based reinforcement learning. First, let's talk about model-free. In model-free reinforcement learning, the agent is can be a policy. A policy is a function that maps observations to actions. So it just is a function which says, if you observe something, what do you do? You can use learning algorithms to learn such a policy, but it requires a lot of data. With a lot of data, you can learn that if you observe something, then the optimal thing to do is a particular action. You can optimize this policy to maximize this objective, which is to maximize the expected sum of rewards. I won't go into details about model-free reinforcement learning, but the other kind of algorithms are model-based reinforcement learning. In model-based reinforcement learning, the agent builds a model of the environment. That is, it builds a model of how the environment works. So if the agent applies a certain action to the environment, it receives a certain observation and reward. So then the agent can mimic that and build a model such that it can think what would happen to the environment if it applies a certain action. With such a model, an agent can imagine that if I make certain decisions, what would happen to the real world. Using such a model, it can plan and imagine without actually doing things on the environment. So it can efficiently make use of data, and by doing this planning, do efficient things without having to do trial and error things on the environment. So in the rest of the talk, I'm going to advocate for model-based reinforcement learning. So why learn these models? Why not just learn a policy function? It is often the case that model-free algorithms tend to require a lot of data, so it's not sample efficient. These are some of the popular works of reinforcement learning: playing Atari games, AlphaGo, and an example robot object grasping task. In these examples and from these papers, you can see that such model-free algorithms requires millions of frames or millions of games or millions of attempts to learn a successful policy. So as I said in the example of the city bikes case, it doesn't make sense if the algorithm takes months to figure out that there should always be bikes at the city center. But then again, it doesn't justify why we should learn models. We should learn models because it's a good inductive bias. Our world operates in a forward causal direction. And from the laws of physics, we know that the dynamics of our world can be really well approximated using a few parameters. For example, Newton's laws of motion and Einstein's theory of relativity are all described by simple equations that can explain or approximate a lot of the dynamics of our world. So maybe we can, in reinforcement learning, estimate these kind of concise models that are quite simple and can describe a lot of dynamics of the world. And also, these kind of models can be efficiently learned using supervised learning techniques. And supervised learning, machine learning techniques have advanced a lot over the last 5 years. So all of those techniques can be used in learning models. So maybe learning and effectively using models of the environment could enable sample-efficient reinforcement learning. So how do we learn these dynamics models? If when an agent interacts with the environment, those interactions results in data. So you see an observation, you take an action, the environment changes, then you see a new observation and you get a reward. This is a data, and through these samples, you can train a model to predict what happens in the environment. So the model predicts that if you see a certain observation and if you do a certain action, certain thing would happen to the environment and you would get a certain reward. So you train your model to mimic what would happen if you applied the action to the environment. And once you have this model, you can imagine certain actions on the model and plan using that, and then take efficient actions on the environment. So this is how you could use, one way you could use models for planning. This is called Model-Predictive Control. Assume you're at a time step t, and the environment or the model is at particular state st. Then you can come up with a random trajectory of actions for a particular horizon at to at plus h. And you can use this model to imagine what would happen if you did these actions on the environment. So if you did these actions, you would get a certain reward from the environment. You can estimate that reward using your learned model. Since these dynamics of the real world is really complex, you need really complex function approximators to model this. And typically, deep neural networks are a good fit for this kind of task. So if a neural network is a model, then this whole thing is a differentiable computational graph, and you can optimize the sum of the rewards to obtain the optimal trajectory that you can take at this situation. And once you've optimized for a particular trajectory, you can apply this first action to the environment, and then the environment changes, and at the next step, you can plan again. So the model doesn't have to be perfect. Since you're always replanning at each time step, this replanning can account for certain errors of the model. But if you use neural networks to do this, it doesn't easily work, because neural nets can be easily fooled by optimizing the inputs using gradient descent. So if you optimize this whole computational graph using gradient descent, then it could result in a certain sequence of decisions which the model thinks would result in a high reward. But if you actually applied it to the real world, it doesn't. These are called adversarial examples. Such examples are really common in computer vision networks, and I assume everybody are familiar with it. So how can we deal with these kind of adversarial examples? One way to do this is to use uncertainty regularization. So you can use an unsupervised learning method to estimate the uncertainty of the states and actions. If you can successfully do this, then you can, when you optimize for your trajectories, you can do it such that you minimize the uncertainty. So the uncertainty estimator prevents this estimation from going towards adversarial samples or like areas where your model is not familiar with. And this could solve this problem. This is based on our latest work in this area, where we use denoising autoencoders to do this uncertainty estimation. So a denoising autoencoder is simply a neural network that is trained to predict clean samples from corrupted samples. So you can take data and corrupt it with just zero mean Gaussian corruption and train the network to decorrupt the data. So it doesn't require any supervision. It's an unsupervised task. And if you use zero mean Gaussian corruptions and make some assumptions, then you can approximate the gradient of the uncertainty estimation using the denoising error of a denoising autoencoder. So this would result in a computational graph that looks like this. So along with the model, you also train a denoising autoencoder with state action pairs. So you collect data from the environment, you corrupt these samples with zero mean Gaussian noise, and then you train the denoising autoencoder to predict the clean data from the corrupted input. And while you plan, you can use the denoising error of the autoencoder and add it to your objective. So now you're minimizing the denoising error of the autoencoder as well as the sum of rewards. And this is a completely differentiable computational graph. And you can use this for planning. So the more details about this algorithm is published in this paper, and it's available on arXiv. It's called Regularizing Trajectory Optimization with Denoising Autoencoders. We tested on a few popular benchmarks in reinforcement learning. First is called cartpole. It's a really classic problem in reinforcement learning. The task is to balance this pole in an upright position along a moving cart. Then in reacher and pusher, the tasks are quite simple. In reacher, it's to move your arm to a particular position in 3D space. And in pusher, the goal is to push an object to a target location, which is marked in red. In Half-cheetah and ant, the goal is to just run forward as fast as possible. This Half-cheetah is a simplified version of the robot that I showed earlier, and the ant is a simplified version of a general quadruped robot. These are some experimental results using this denoising regularization on these benchmark problems. And you can see that these results are shown for just 10 episodes. It's common that in reinforcement learning, results are shown for hundreds or thousands or even 10,000s of episodes. Here we show that we can effectively solve these tasks in just a handful of episodes. It's easier to show videos than explaining these numbers. So I'll show them soon. These are results from a really popular model-free algorithm called Proximal Policy Optimization. It's been used in a lot of popular works that have received media attention lately. This is the result if you apply Proximal Policy Optimization on the Half-cheetah task. It obtains a reward of approximately 2,000 after it's been trained for 1,000 episodes. Here in the Half-cheetah results, you can see that it obtains a reward of above 2,000 in just 10 episodes. So what do these numbers mean? This is the cartpole task. So this is after 200 steps of training, which is just really maybe a couple of seconds of data. This is after 400 steps of training, which is like 4 seconds of data, I think. And you can see that it has already learned how to successfully balance the pole. It used to be that Gaussian processes or such models are typically used for really low dimensional problems like cartpole. But here you can see that even using a neural network with absolutely no regularization can perform successfully on the cartpole task. And these are our results on the Half-cheetah task. Here, the controller is just applying random actions to the joints, random torques, and observes what happens to the environment. So this is about, by doing these random actions, it collects about 1,000 samples. And using those 1,000 samples, we train a model and a denoising autoencoder. And from here, we start planning with the model. And you can see that after just 1,000 steps of training, it tries to run forward as fast as it can, but it doesn't try really unrealistic things because the denoising autoencoder prevents it from doing so. And after just 5 episodes or 5,000 steps of training, it has learned a fairly successful gait of running. And after about eight episodes, it can run quite well. I would say it can be considered, the task can be considered solved with such a running gait. And these are our results on the ant environment. And this is after 10 episodes of training. So in Half-cheetah and the ant, 10 episodes of training corresponds to about 8 minutes of data. I mean, can you imagine that you just build an ant robot, but you don't know anything about it, but you just plug in this algorithm, and within 8 minutes, it's already walking. And it's all walking quite well too. Yeah, so here we demonstrated this model-based reinforcement learning in some toy benchmark problems, but there are a lot of open problems to be solved before we can apply it in a real-world scenario. But in conclusion, I believe that we need these kind of model-based reinforcement learning algorithms if we want to solve AI. Yeah. Thank you for your attention. Any questions?
Thank you, Rinu.